Hello folks, welcome to my video. This video is gonna be quite long, but I would like to make it simple for you. Cause I would like to share one of my experience with system design, and right now I'm at system validation and in system simulation actually. So I'm not going to share a lot of about the systems engineering. But the system engineering, if you let me to explain to you, it's basically I have to open a Word file. Systems engineering, I'm not going to give a definition because it's quite I'm not able to give a definition, but I can make you understand what is it actually. So as I'm an automotive engineer, so everything that I think or do my work or in my thought is everything is automotive systems, right? Automotive systems. In automotive systems, you have it's system of systems. Now these jargons probably go beyond of your mind, but I'll try to make it an easy explanation. So in automotive system, we have different system. Let's say we take a system for an example, powertrain system. So we have a system objectives. System objective, like what should the system function perform, right? It shall provide required traction force to propel the vehicle, right? To propel the vehicle. For example, we have a motorcycle, and the motorcycle need to be rode for an example 70 kilometer per hour, and your powertrain should provide this enough power to propel the vehicle at this speed. For example, you should have a good engine for that, your transmission, maybe your chain sprocket. Anything can happen with this powertrain. So the system has a core objective there. Let me zoom it. And then it should have a good performance, which I've talked a little bit about it a couple of seconds ago. It should be efficient, right? So what it should be or it should not, it depends on the specific requirements. Let's say I write it right here, write the requirements, right? Requirements are what we want, what we expect from that system, right? We want the motorcycle should propel, the motorcycle should reach the top speed 70 kilometers per hour. That's a requirement. That's a functional requirement. So we have n number of requirements there. For example, a rider has a requirement to have his seat more spacious and comfortable. So we have requirements, and those requirements should be met, and then we can say that the system has been designed properly, right? You do the requirement, and then you study the concept, like how should the system should be, how the system should. For example, based on the requirement, we can decide which type of engine we want to use. Either the vehicle should have a lithium-ion battery or lead-acid battery. If it's an electric one, obviously, whether you should use a PMSM motor, BLDC motor, whatever it is, you should go for a study concept and then prepare logical decomposition. Yeah. Now what I mean is that the logical decomposition is that you first start with the requirement. The system is a powertrain system, and you have a different subsystem, like the engine subsystem, Then you have the gearbox subsystem, right? Because these subsystems, these are the subsystems of a system here, powertrain system. And then when you go more detail there, you can have a component level. So we have system level, subsystem level, and then component level, part level, whatever it is. So when we see this whole system in a hierarchical model, um, we see the architecture and we say it's a logical decomposition. So your powertrain requirement has 70 kilometer per hour requirement, and now you're gonna calculate and analyze what the engine should specifically perform, right? What should be the engine's power output if you want to catch this top speed, right? So when we analyze from system to subsystem to component and part, and we say that this is logical decompositions, and you have your architecture here, right? The basic modeling of that system. And when you make the system, now you simulate the system, right? You simulate the system. When you simulate the system, you perform actually the integration, right? Don't take it take it for granted. I'm not an expert in system engineering. I'm still a student. I'm just sharing my own experience, right? Because you find a lot of textbooks and a lot of tutorials there. Maybe a lot of things can be seems quite confused, but it is what it is. What I have experienced actually. And when you integrate, that's mean your whole system perform good or not. That's called integration, right? I mean, when you make two components together, if they're working perfectly or not. And then you have your validation and verification. Validation and verification is the system, have we built the right system, right? Have we built the right system, or the system have built right? So this is a little bit confusion can arise, but the validation is the against the requirement. If you have met the requirement, that's your system is validated. And if you have made in a right way, that's you have to do the verification. So we use a V model, we call it a V model. We have this left and right, a lot of things there. I'm not going to share this thing. Probably gonna take a lot of time. So the first thing that I did recently with a company project in my internship, I first took the mission objective here. You see the mission objective, so I have written every information here. I mean the word of mouth that I've written here. For an example, from the stakeholder, the company who wants me to design the system, they told me that okay, this bike should have performed this. And then I analyze the constraints, like there is a budget constraints, power constraints, and then you have the design drive, like the influencer of that design. What can really influence in your design? And then I did operational objectives and criteria for mission success. So this is called the mission objective study. So we have done a mission objective study, and then steps 2, we build a ConOPS, that operational concept. What can be the operational scenarios there, like why they want to build this bike in this way, right? So we had to analyze different expectations from company expectation, investor expectation, government expectation, the rider perspective. We had to analyze this thing, and we had to keep a note. And then in step 3, we finally came to the requirement elicitation. From mission objective and operation concepts, we come up with the requirements here. We have a different requirement. I'm not going to share this thing with you. Maybe one or two, maybe I can share. From safety feature, we have requirements like stable at low speeds. It should be stable at low speed because it will have a lot of loads with it. because it's a delivery bike. So it should be stable because it's going to weight a lot more wages than a normal bike or normal motorcycle. So it's one of non-functional requirement important for stop and go city traffic, right? And then after that we went to, I mean, I have did my own one, and then I did the expectation validation, whether the requirement is right or wrong. I had to validate with the expectations of the stakeholders, and then I build a measure of effectiveness, like how can I really judge if the analysis or if the requirement is right or wrong, because your requirement can be wrong and then you can build the wrong system. And then in the step 6 you can see the technical requirements. In here I soak out the technical requirement from the requirement. Like for an example, if you see here, the bike must travel between 80 to 100 kilometer per one single charge. Like if you charge for one time in one charge cycle, the bike should have covered the 80 to 100 range. So this is called the technical requirements you have, and then I have the baseline technical requirement, the baseline technical requirements, and technical requirements has a great distinct. The baseline is the fixed and the final one. You're not going to change these requirements until you have another loop. And then I go to the measure effectiveness, which I've talked already. These are the parameters. In against I will validate my requirement. And then the last is the logical decomposition. The logical decomposition has, which is the system level or subsystem level. You can see the requirements are very precise, like for performance and drive system, I need top speed for 60 km per hour, the acceleration, the payload capacities. Everything here is technical and detailed and constrained, very, how to say it, very organized. So up to this, I have my documentation work here. Remember, in the real companies, I mean, I have to work in a real company, but in the big project, my project is very simple, but it's a big project. They have one dedicated, maybe more than 1 or 2 or 3 requirements engineer. They spend a lot of time just to do this work. But in my case, as I'm doing an internship, so I don't have a much load on it. So I did it by myself because it's quite simple. Not simple for me, but it's not so very complex that you have to spend a lot of time. So I'm going to share the system that I designed here and did the simulation. I'm still in my validation path. This is the vehicle dynamics block. I have a electric motor here, DC-DC converter. It's a very simple electric powertrain, right? So I simulate it. Somehow my simulation is not right at this point, but I can still manage. In my simulation, I can see these speeds in kilometer per hour, in the mile per hour, and the distance coverage, how I can cover the distance now. I'm at this point validating my simulation result. If it's actually, so you have another part here called a test. In Simulink you can do the testing, but to be honest, like we have a design verifier here, so you can generate the test cases against your performance, against your efficiency and stuff like that. And then you can go and check the Simulink test, right? You can test here. You can build your test cases, test harnesses, it's called. Like you can literally have a test of hardware in loop, software in loop. And in this way you can test your system. So as a system engineer, or as a student system engineer and student, this experience really gave me a lot of like confidence here, because in MATLAB you have to do like coding and stuff like that, these strategies and speak commons. I'm not going to like talk a lot about this. Okay, so you should have a really good understanding of math and logical thinking and algorithm and stuff like that. So this is all my experience about my system engineering project. Thank you very much.